Hey, how you doing? We are continuing to look at volume by rotation or volume by revolution, and today we're looking at cylindrical shells. Now, a quick note, these are not, that's my eraser, I changed my icons. These are not tested on the AP exam, but if you were taking a traditional Calculus 2 course in a college or university, you would see this particular topic. It's actually really useful for certain volumes that you could otherwise solve with a disc or a washer, depending on the shape, but it's a little bit different. So what we actually start with is this cylinder, but it's an empty cylinder. So think of like a pool noodle or something, but the hole, if the kind that has the hole in the center, but that hole is really, really large. So you have this outside piece like this. And if you cut this down the side, you would open it up and have a rectangle. And so what happens with the cylinder method, the shell method, is that you have these different layers stacked up one inside of another. So down here, it kind of just shows you what's going on, but you'd have a layer on the outside, and then you'd have a layer on the inside, and another layer on the outside, another layer on the outside. So you would have all of this happening, and you get this 3D shape. And it's really kind of cool. But the idea is, instead of having that area, the cross section, like we did with discs, washers, and slicing, we have the area of this rectangle. And so the base of this rectangle is actually the cylinder's circumference. So this is 2 pi r, and then the height. And so when you integrate that, here's your 2, here's your pi, x is really your r, and f of x is your height. Looks kind of like that. And again, dx is your thickness of each of those rectangles, each of those sliced up together. I'll see if I can break in here with a little video and give you a demonstration. But let's kind of jump right in. Find the volume of the solid generated by revolving the region bounded by the graph of y equals x squared plus 2x, the x-axis, and the line x equals 1 about the y-axis. So if we were talking about discs and washers, this would be a washer problem. There would be holes inside. Those slices would be perpendicular to the axis of rotation. But we're talking about shells, and shells are parallel to the axis of rotation. All right, so as I was saying, shells are parallel. So this particular example has everything together for us, which is pretty nice. Let me just double check something. Okay. So we're going to find the volume of the solid generated by revolving the region bounded by that graph, the x-axis, and the line x equals 1 around the y-axis. And so it started to say that this would be a washer if we were dealing with discs and washers. And then it would be a dy problem. But because our slice is vertical, Bob's vertical, so this is still a dx problem. Now, I had stopped a few of us from making the conclusion that, oh, if we're rotating around the x-axis, then it's a dx problem. This is why I put the brakes on that conclusion that we were trying to make, some of us were trying to make. Go back to Bob, go back to those slices. If they're vertical rectangles, it's a dx problem. If it's horizontal, it's a dy problem. And it doesn't matter if you're doing area, it doesn't matter if it's volume by slicing or discs or washers or shells. Vertical slices are dx, horizontal slices are dy. So let's use our formula. The volume is 2 pi, that's the difference between discs and washers, from A to B. Well, it's pretty obvious on this picture. We go from 0 to 1. Your radius, they have just x in here. I'm not loving that because you can always rotate around something different, but I'll use it for now. The radius is whatever the distance from the axis of rotation is. And so in this case, it's the x coordinate. I'll go with x. And then f of x, that's your height. So Bob in this picture, where's Bob? Bob is the height. And I also tried to be wary of, or aware of the fact that Bob's representation isn't perfect. And that's because it's always a little bit different what Bob stands for. So in this case, Bob would be our head minus our feet. Bob's the height here, where in other disc and washer problems, it's been the radius. So we have something like this. You don't have to square it, and it's a dx problem, all right? I didn't bring my calculator with me, which is a bit of an oops, but you could easily, I guess I'll go up here and do this, distribute. So volume is 2 pi between 0 and 1, x cubed plus 2x squared. 0 times x is still 0, 2x, or dx rather, x to the 4th over 4, plus 2x to the 3rd over 3, between 0 and 1. This is a 2 pi problem. In the front, put our boundaries in. This becomes 1/4 plus 2/3. Luckily, that 0 makes everything 0, which is handy. So 1/4 plus 2/3, 3, 8, 11/12. 2 pi and 11/12. And what do we have here? Let's reduce 11 over 6 pi. If you get something different, let me know. But that's what I have for the volume. Good. Truthfully, you all can use Math 9 very, very well. What you need a little help with, or what I'm teaching you, is how to set up the integral. That's the new part for today. So example 2, find the volume if the solid generated by revolving the region bounded by f of x equals x squared and 12 minus x to the right of x equals 1 about the y-axis. So I know f of x is equal to x squared. Let's pick a color. F of x equals x squared. G of x is 12 minus x. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Did I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12? I missed my spot. 12 minus x is a line that comes down. G of x equals 12 minus x. And to the right of x equals 1, so here's x equals 1. Oh, good. This is one that's not on the axis of rotation. That's what I was trying to talk about before. And we're going to rotate around the y-axis, which is over here. So if we're talking about shells, shells are parallel to the axis of rotation. So they are going to be vertical slices, which works out well for us here because all the heads, where's Bob? What about Bob? All the heads line up with that pink line and all the feet line up with the purple parabola. If this were a disc washer problem, it would be a washer. It would be horizontal slices, and you would need 2. The bottom half would get 1, and the top half would get another. So volume is 2 pi. Where do we talk about A and B? Well, A is definitely 1. But B, if we were in class together, I'd say, how do we find B? And you would tell me that that's where they intersect. So I'll set F equal to G. So x squared equals 12 minus x. X squared plus x minus 12 equals 0. So I have x plus 4 and x minus 3. So x is equal to 3 and negative 4. How come I have 2 answers here? Because it's x squared, it's talking about the other half of the parabola up here. We're not interested in that value. We actually want the 3. And to get the y-coordinate, I'd square it'd be 3, 9. I don't think we'll use the 9 anywhere, but that's okay. So we integrate from 1 to 3. Now, radius, I am still rotating around the y-axis. So even though the shaded area doesn't go all the way to the y-axis, your radius is still just the x-coordinate. You know, this bob has a radius of 2. There's a radius of 2.5 and a radius of 1.5. All the different radii between 1 and 3. So your radius is just the x-coordinate. Now, when we talk about the height of each cylinder, that's Bob's height. So where's the head? The head is at 12 minus x. Where are the feet? The feet are at x squared. Like this dx problem. You can definitely use Math 9. You can also distribute this one. It's pretty easy in this case. I have negative x cubed minus x squared plus 12x dx. All right, cool. At this point, you would find the antiderivative, you'd put in the 1 and the 3, and you'd have the answer. I didn't leave my calculator with me, and I want to keep this video going. So go ahead, figure out what the volume is, and just like if we were in class together, talk to your neighbor, see if you get the same thing. I guess those are my only examples. Look at that. I did find this graphic online, though, that I liked because it compares the disk method and the washer method and the shell method, and it kind of puts everything together. Remember your typical element? That's Bob. Bob. This would be a dx. This would be a dx. If Bob goes side to side, this would be a dy. This can change. Well, I guess this whole thing is revolving around the x-axis. Remember, if you're revolving around the y-axis, everything would be flipped around a little bit. And here's just a picture. Your disk would be slices like this, versus your shell would be a little bit different. So I guess with the shell method here, I was all ready to do some much more complicated examples, but they're not included. These are straightforward examples. So that's good. That's good for all of us. Let me go back and finish this one up then. I thought we had more to do. Got negative x to the 4th over 4 minus x cubed over 3 plus 12x squared over 2. This is between 1 and 3. Negative 3 to the 4th power, 3 times 3 is 9 times 3 is 27 over 4. 3 to the 3rd power. That's not right, is it? Nope, this should be 81. Minus 27 over 3 plus 12 times 9 is 108 over 2. I'm definitely not going to get this done in my head, am I? Minus 1/4 minus 1/3 plus 6. All right, let me pause this and I'll be right back. All right, I cheated a little bit and pulled out Math 9. So here we go. That's how I entered it. All right, when I hit enter, I have 19.3 repeating. So all of this we're going to assume is 19 1/3, except I'm off the paper. All right. And let's just verify the other one up above, the first example while we're at it. 0 to 1. I'm a little disappointed. Oh, no, wait. What did I forget in the last example? I didn't multiply it by 2 pi, did I? Nope. All right, 121. Now that I've made a total mess here, let's just get rid of all this. All right. Volume equals 2 pi 19 1/3, which is really 121.47. Sorry about my completely sloppy, not overly professional video here. And let's just double check the first one. The first one would be Math 9, 0 to 1, x, comma, x squared plus 2x. And a dx problem. 0.916. And then if I times that by 2 pi, 5.75. Equals 5.75, which I think is going to be about what we had before. That should match. All right, it does. Okay, there you go. A quick introduction to the shell method. If and when you take Calc 2 in college, you'll do a few more examples of that. I really like the shell method, so I'm sorry we're not doing more, but There you go. Because this is a short lesson, work on assignment 8.3 and then go back and finish up the other ones. I'm sure you have a little bit more there to do as well. See you soon.